Chapter 1 Real Numbers, Exercise 1.2, Exercise and Example Problems. So first comes the theorem. Theorem 1.2. Okay. This theorem statement is important for you, which you are going to apply in many of your exercise problem. So the theorem proof is not important for the exams. It's not usually asked in the exams as a proof. So, but the theorem statement is important for you, which you want to write in the following exercise problems. Okay. So first we want to know how they are proving the theorem. Okay. Let P be a prime number. If P divides A squared, then P divides A. So when we are reading the theorem statement, it gives that P a prime number. So I'm considering a prime number 2. Okay. And P divides A squared. I'm taking a perfect square number 16, which can be divided by 2. So it's given that P divides A squared. You are taking a prime number and another number, perfect square number. The prime number can be divide that square number. Then what we want to prove is the prime number can divide the A also. If 16 is A squared means this is our A. If 2 can be divide 16 means 2 can divide 4 also. That is what we want to prove. Okay. So where A is a positive integer. So here A can be, that means the 16 can be written as the factors like 2 times of 2 times of 2 times of 2. This one is 4 and this is 4, which means that the 4 is our A. Okay. Here it is shown you how the factors has been written, as I have written 2 times of 2 times of 2. Here the factors of 16 has been shown to you, and 16 is equal to 4 times of 4. Otherwise 2 times of 2 times of 2 times of 2, like that it has been shown all the prime factors. Okay. And P divides A squared. P divides A squared means, as I said, if 2 divides 16, then the fundamental theorem of arithmetic. What's the fundamental theorem of arithmetic proves us? If a composite number factorized, the factors what we are getting is unique, irrespective of their orders. So 16 can be factors like 2 times of 2 times of 2 times of 2, where I have taken 2 is the prime number to divide it. You can see here the factor, one of the factor of 16 also 2. So definitely 16 can be divisible by 2. That is what written over here. Since 16 can be divisible by 2 means P is one of these factors, definitely the P can be divisible by the P divides A also. So P that means A is our 4. So definitely A can be divisible by the prime number 2. Okay. Just this is only for the understanding. The theorem statement one more time. Let P be a prime number. If P divides A squared, then P divides A. Okay. Which means when 16 is a composite and perfect square number, if it can composite number, if it is divisible by a prime number 2, then definitely 4 also can be divisible by 2. A squared divisible by P, then A also divisible by P. This is our theorem. Okay. Let's go for the question number 1 example. Before we are going for the example question, we want to know what is a rational and irrational number. Okay. So here I have the rational numbers. We know that which numbers can be written in the form of rational numbers means which you can write in the form of A by B, where B not equal to 0 and A and B are integers. This is okay. This is the definition for the rational numbers. When a rational number, when you are taking a rational number in the form of A by B, when you are dividing A by B, if your quotient, if your answer is non-terminating and non-recurring, then these numbers are said to be the irrational numbers. Then these numbers said to be irrational number. For example, when I am dividing a number, if my quotient is like 0.12347 like that, there is no repeating digits. At the same time, it's not terminating also. This type of decimal expansions or decimal numbers are known as the irrational numbers. So this is the type 1 of irrational numbers. What is the type 1? Non-terminating and non-recurring. Whereas some numbers you may notice that the certain set of numbers may repeating. So this you can write like 0.12 bar, which means that 1, 2 is keep repeating and non-terminating also. So when a set of numbers or a single digit is keep repeating means they are said to be non-terminating but recurring. Okay. When non-terminating recurring means these numbers are said to be rational. Okay. So only one condition, that is non-terminating and non-recurring, means those numbers are said to be irrational numbers. One more example, 0.1, 0.01, 0001 and 4 zeros 1 and 5 zeros 1. Here you can see that there is no, the certain pattern is there in the decimal expansion, which is repeating here, and it is non-terminating also. So these type of numbers are said to be irrational numbers. Okay. Next type of numbers, type 2 of irrational numbers. Take a letter M. I'm taking a letter M as a positive integer. Okay. Positive integer. At the same time, M is not a perfect square number. M is not a perfect square. So if this is the number, M is a positive, at the same time M is not a perfect square number, means these numbers are said to be irrational. For example, root of 4. We know that 4 is a perfect square number. Okay. Then what is the square root of 4, which is equal to 2? So definitely the root 4 cannot be the irrational number. At the same time, root 3. 3 is not a perfect square number. So root 3 is irrational. So many examples we can say like root 7, root 11, root 13. So these 11, 7, 13 are non-perfect square number. At the same time, root 8. Root 8 can be written as 2 root 2. So 2 root 2 again, root 2 is irrational. So 2 root 2 also irrational. Root 8 is irrational number. So any number, okay, within a square root symbol, if the number is not a perfect square, then those numbers are said to be the irrational numbers. So type 3 irrational number means cube root of M I'm taking, where M is the same integer and where M is not a perfect cube number. If M is not a perfect cube number, then these type of numbers are also said to be the irrational number. For example, cube root of 27 means we know that cube root of 27 is 3, because 27 is 3 times of 3 times of 3 is 27. Okay, so 27 is a perfect cube number. Instead of 27, if it is cube root of 21 means, then this cube root of 21 is the irrational number. Okay, and then another type is type 4, which is pi. We know that pi is irrational number. How pi is irrational number? We know that pi can be written in the fractional form 22/7. 22/7 is in the fractional form. In the decimal form, it is 3.14 and it keep continuous. It's not terminating. For our convenient, this is only approximate value only. Okay, and 3.14 also approximate value only for our calculation purpose. To make our calculation easy, we are taking only 3.14 only, but actually it is non-terminating and non-recurring decimal. So pi is also an irrational number. Okay, I hope you understand the rational and irrational differences. Now we are moving to the example questions. Okay, in the example question, first it is given that prove that root 2 is irrational. Actually, it is given as a theorem, but it's a same type of example question only. Root 2 is irrational. How to prove root 2 irrational? So the method what we are using is known as the contradiction method. Contradiction method means we know the fact is root is irrational, but we are going to assume in the wrong way, that is root 2 is rational. Then finally, according to the result of our assumption, the result may go wrong. So from there we will say according our assumption is wrong. So root 2 is irrational. Like that we are going to prove using the contradiction method. Okay. So first let us take root 2 is rational. When a number is rational, it can be written in the form of a by b. Okay. So root 2 is a by b. We know that when we are writing in this form, definitely you want to say AB is in AB. A and B are integers and B not equal to 0. Okay. Here one more condition we are adding, where A and B are integers and B not equal to 0. At the same time, A and B are co-primes. Okay. Co-primes means no common factor other than 1. For A and B, there is no other common factor. For example, 4 and 5. They don't have any common factor. If this is 4 and this is A and 5 is B, means they don't have any common factor. 2 and 5, they don't have any common factor. 7 and 11, they don't have any common factor other than 1. So such numbers are A and B. Okay. And then multiply this root 2 with B. It is root 2B is equal to A. Squaring on both sides. When we are squaring on both sides, root 2b the whole squared equal to a squared. This power 2 distribute to the two items inside the bracket. So when you are squaring the root 2, this power and this square root symbol and the power 2 will get cancelled. It will become 2. So 2b squared is equal to a squared. Okay. 2b squared is equal to a squared. So 2b squared is equal to a squared means we keep the b squared here and bring the 2 to the next side. It will become a squared by 2, which means that 2 is a prime number which can divide a squared. So 2 divides a squared. Now recall the theorem what we have learned. If a prime number p divides a squared, then p divides a also, where a is a positive number. So using that theorem statement, we are proving that 2 divides a also. Mark it as equation number 1, and then we are going for the second part of the proof. Till that, consider it is the first part of the proof. Now second part of the proof as follows. When a number divides means definitely we will get a quotient. Let's consider C is the quotient. Do multiply like this, then A you will get 2C. This A equal to 2C, substitute over here. Okay. So when we are substituting, 2b squared is equal to a squared. In the place of a squared, put 2c. So 2c the whole squared is equal to square the 2 as well as the c. It will become 4c squared. And then bring the 2 to the next side, like b squared is equal to 4c squared divided by 2. Cancel these two. So 2c squared, b squared is equal to 2c squared, which means that, like here, 2b squared is equal to a squared, which means that 2 divides a squared. And here, b squared is equal to 2c squared, which means that 2 divides b squared. Actually, note this point, 2 divides A. Here it comes 2 divides B squared according to the theorem statement. 2 divides B also. So from 1 and 2, 2 divides both A and B. But what we have considered like A and B are co-primes, they don't have the other common factors than 1. But here it comes that 2 is also the common factor for both A and B. Okay. So this is, that is A and B cannot be co-prime. Our assumption is wrong. Therefore, root 2 is irrational. The same set of lines only you are going to write for all the proof, like proving root 2 is root 3 is irrational, root 5 is irrational. So, if possible, memorize those statements. Okay, it will be more useful for you to write for the other numbers also. Now, root 3. So, what we will do? According to the contradiction method, we'll consider root 3 is rational. When a number is rational, it can be written in the form of A by B, where A and B are integers and co-prime and B not equal to 0. When root 3 equal to A by B, do the multiplication like this. Root 3 B equal to A and square on both sides. So root 3b the whole square is equal to a square means when you are squaring this one, you want to apply the power to both. So root 3 will become 3 and it will become b squared, which is equal to a squared. From here, we are going to write like a squared divided by 3 is equal to b squared, which means that 3 divides a squared. From the theorem statement, we can say when 3 divides a squared, 3 divides a also. When 3 divides a also, it will give you a perfect number as a quotient. Take it as C. So a divided by 3 equal to C. Do cross multiplication, a is equal to 3C. Put this a is equal to 3C here, like 3b squared is equal to a squared. Here you want to apply, instead of a, replace 3c. When you are replacing a by 3c, so 3c the whole squared will become 9c squared. Okay, so 9c squared and this 3 will come to the next side as division. Cancel this, it will become b squared is equal to 3c squared. B squared equal to 3c squared means b squared divided by 3 equal to c squared, which means that 3 divides b squared also. Before what we got is 3 divides a squared. Now what we are getting is 3 divides b squared, which means that 3 divides b also. So wherever you are using these two statements, definitely you want to write the theorem statement also. Okay, otherwise you can do one thing, write the statement, theorem statement the first time and mark it as star like this. And here you can use like using like that you can mention, but more proper thing is writing the statement. 3 divides b also, and from 1 and 2, 3 divides both a and b, which means that other than 1, a and b have the one more common factor, which is 3. According to our assumption, it's not correct because a and b are co-primes. But here we are getting 3 is a factor for a and b. That is, a and b cannot be co-primes. So our assumption is wrong. Therefore, root 3 is irrational. Okay. So now, already we have proved that root 2 and root 3 as irrational. Now, when some numbers or some other addition or subtraction with the irrational number, whether it will become rational or irrational. So root 3 is a irrational number. If I'm adding a rational number 5 with that also, it is irrational only. Okay, if I am multiplying a rational number with the irrational number also, again it will be irrational only. So whatever you are doing the calculation with the irrational number, the final answer you will get only the irrational number. Only when you are squaring a irrational number like this, it will become rational. Okay, so now you look at the question. 5 minus root 3 is irrational. That is what we want to show now. So consider like according to our contradiction method. First you will take 5 minus 3 is rational. So 5 minus root 3 can be written in the form of a by b, where a and b are the integers and b not equal to 0. At the same time, they both are co-primes. Keep the minus root. So 5 minus root 3 is equal to a by b. Keep the minus root 3 here and bring the a5 to the next side. To remove this negative, multiply the negative 1 on both sides. Multiply by negative 1 on both sides. So what will happen? Root 3 is equal to, the negative 5 will become positive and positive a by b will become negative. Okay. Now you can see here 5 minus a by b, do the cross multiplication. So 5 minus a by b, it will become 5b minus a. Since a and b are the integers, 5b minus a by b is a rational number. But root 3 is irrational, we know. However, root 3 can give you the rational value. Okay, is rational. But root 3 is equal to 5b minus a by b. This is irrational. This is irrational. So definitely they both cannot be equal. They are not equal only. So this is a contradiction. Our assumption is incorrect. Therefore, 5 minus root 3 is irrational. Follow the same method and same statements for the rest of the problems also, where you want to prove some numbers are irrational. Okay, so 3 root 2 is irrational. For 3 root 2 is irrational, consider it as rational, and then write 3 root 2 is equal to a over b, where a and b are integers, co-prime, and b not equal to 0. Keep only the root 2 here and bring the 3 to the next side. So when you are bringing the 3 to the next side, it will come to the denominator like root 2 is equal to a by 3b. Here, a and b are integers, so definitely a divided by 3b also rational. But we know that root 2 is irrational. So definitely irrational number cannot be equal to the rational value. Our contradiction, because of our contradiction, we are raising to this result. So our assumption is wrong. 3 root 2 is irrational. Okay. Next is exercise 1.2. Prove that root 5 is irrational. Just keep the steps what we have written in the root 2, root 3 irrational problems. Follow the same steps. First, assume that root 5 is rational. Since root 5 is rational, which is equal to a by b, and a and b are co-primes and b not equal to 0, and root 5 equal to a by b, a is equal to root 5b. Now, squaring on both sides, when we are doing the cross multiplication, root 5b equal to a. Squaring on both sides, root 5b the whole squared is equal to a squared. When you are squaring a square root number, it will become 5, and b will become b squared, which is equal to a squared. From here, we can understand that a squared divided by 5 is equal to b squared, which means that 5 is a prime number, which is a squared, which divides a squared. 5 is a prime number which divides a squared. So according to the theorem statement, 5 divides a also. Five divides a also. Now we are going for the second part of the proof, like 5 divided by, that is 5 divides a also means a divided by 5, we will get some quotient. Do multiplication like this. So a is equal to 5c. This a is equal to 5c, we are going to apply in 5b squared equal to a squared. Here we are going to apply that in the place of a. apply 5c. When we are applying that, it will become 5c the whole squared is equal to 25c squared, because you are squaring 5 as well as c. 5b squared is equal to 25c squared. So this 5 will come to the next side. So b squared is equal to 25c squared divided by 5. When you are cancelling, it will become 5c squared. So b squared is equal to 5c squared, which means that b squared divided by 5 is equal to c squared. That is, prime number 5 divides b squared. Prime number 5 divides b squared. When prime number 5 divides b squared means, according to the theorem, 5 divides b also. Already we have proved that. Already we proved like 5 divides a. And here it is coming like 5 divides b, which means that 5 is common factor for both a and b. But what we have assumed at the beginning is a and b are co-prime. They don't have any other common factor other than 1. But here 5 also one of the factor, which means that they cannot be the co-primes. So our assumption is wrong. Root 5 is irrational. Question number 2. 3 plus 2 root 5 is irrational. So let's start proving this one. 3 plus 2 root 5 irrational. So 3 plus 2 root 5 initially we are assuming like rational. If it is rational, 3 plus 2 root 5 is equal to a over b, where a, b are integers, co-prime, and b not equal to 0. So here 3 plus 2 root 5 equal to a over b, 2 root 5 equal to a over b. This positive 3 going to the next side, minus 3. 2 root 5 is equal to a minus 3b divided by b. So root 5 is equal to, this 2 is in multiplication, which will go to the denominator as 2b. Here, a and b are integers. Since a and b are integers, this is rational. But root 5 is irrational. So irrational cannot be equal to the rational value. Okay. This contradiction has arisen because of our wrong assumption, like 3 root 5 is rational. Therefore, 3 plus 2 root 5 is irrational. Okay. Next, the same type of question, 1 by root 2. You want to know the perfect statements. That's why I have attached the statements over here. You can see here 1 by root 2 initially we are taking. We are considering as like the previous question, 1 by root 2 as a rational number. So 1 by root 2 is equal to a by b. We know root 2 is irrational. So do the reciprocal on both sides. So root 2 is equal to b by a. Since a and b are the integers, a over b or b over a, both will give you the rational answers. Okay. So b by a is rational. And if b by a is rational means, which means that root 2 also rational. But it is not possible because root 2 is irrational. Because of our incorrect assumption, 1 by root 2 is rational. We arrived to this contradiction. Therefore, 1 by root 2 is irrational. Okay. You may notice that mostly all set of statements are same. According to the given question number only, here and there some changes are happening. Otherwise, the statements are almost the same. 7 root 5. So how to prove 7 root 5? First, we will assume 7 root 5 is equal to a by b, which means that 7 root 5 is a rational number we are taking. So keep the root 5 over here and 7 will come to the denominator like 7b. Okay, here a and b are integers, therefore a by 7b is a rational number, but root 5 cannot be the rational. Root 5 is irrational, so root 5 cannot be rational. This contradiction has arisen because we have assumed that root 5 is rational. Okay, our assumption is wrong, therefore 7 root 5 is irrational. So in these type of questions, there is no much calculation part, only the statements you are writing. So when you are presenting these type of answer, all the required statements like assume that 7 root 5 is rational, where 7 root 5 equal to a and b, where a, b are integers, co-prime, and a, b not equal to 0. Like these statements are very important. Okay, don't skip any of the lines. 6 plus 2 root 2 is irrational again. So we know that we are using the contradiction method. Assume that 6 plus root 2 is rational. So 6 plus root 2 can be written in the form of a by b, where a, b are integers, co-primes, and b not equal to 0. So 6 plus root 2 is equal to a by b. Root 2 is equal to a by b minus 6, which is equal to a minus 6b over b. Okay, 6 times of b, 6b over b. Root 2 is equal to this one. And since a and b are integers, a minus 6b minus b gives you the rational answer. Is rational. So root 2 cannot be the rational because we know that root 2 is irrational. This contradiction has arisen because of our wrong assumption, like 6 plus root 2 is rational. Therefore, 6 plus root 2 is irrational. Okay, that's it, our exercise 1.2. I hope you all understand the explanation well, and we will meet in the second lesson, polynomial. Thank you.